All right, folks, back here with another video in our study of the derivative, where I think in this video we're probably going to approach the derivative calculation a little differently. We're going to introduce ourselves to the idea of what's known as implicit differentiation. And through implicit differentiation, trying to fix my camera here, through implicit differentiation, we're going to be able to then develop a few things. We're going to be able to develop, first of all, our derivative rules for the cases of, what is that going to be? Inverse trigonometric, or not just inverse trigonometric, but inverse functions in general, which for the case of exponentials, or the natural exponential, is going to give us the natural logarithmic functions derivative. And once we have the natural logarithmic functions derivative, we'll actually be able to define the derivative for all logarithmic functions. Once we have the derivative for all logarithmic functions, we can then use implicit differentiation to talk about the derivative of all exponential functions. So while working through our exponential and logarithmic derivative formulas, we're going to use some implicit methods because of the inverse relationships. And then also with our inverse trigonometric functions, we're going to develop some rules there, and the rules are going to all develop using some implicit methods. And then on top of that, we might think of as our implicit methods and the case for, they're going to develop from the case for chain rule, are going to give us a way of taking our derivative results that we've stated very specifically for specific cases of functions and be able to generalize them. All right, be able to generalize them for those function types involving compositions. And we'll get all there. That won't be in this video, folks, nor will any of that exponential or inverse trig function behavior for the derivative. What we'll see, those are later videos. What we're just going to introduce here is the concept of the implicit differentiation. So let me bring my notes up here. I do title this just implicit differentiation. That is where our focus is going to be on this set of notes, is how to perform this process. And then we will see this process used a few other places here in the future, as I've mentioned. Now, where we begin is just by noting, what do we mean by being implicit versus the term explicit? And that has to do with that in algebra, some relationships between two variables are expressed explicitly as functional relationships. We can explicitly use that notation maybe where y equals f at x. We can explicitly use function notation. And there are some relationships also, though, that happen in algebra between two variables where things cannot be expressed explicitly in a functional relationship, and what we have is more of an expression that is implicit, right? It is an implicit relationship between our two variables, all right? What do I mean by that? Well, let me bring in some example here. For example, y equals x squared plus 3x minus 5, well, we recognize that as a quadratic function. And specifically here, y is being expressed explicitly as a function of x. And we could say in this particular case for y is that y is equal to f of x. And we can substitute f of x into that equation for y and express explicitly this quadratic behavior as the functional behavior for the quadratic function, where we can say that this is all equal to f of x. This is an example of an explicit function. Whereas what do we mean by an implicit relationship? Well, we might consider the relationship describing the unit circle. This relationship where x squared plus y squared equals 1. Here we have a relationship between the two variables x and y, But this relationship does not express the relationship between x and y explicitly as a functional relationship between these variables. The relationship here is rather implicit. We can't necessarily substitute in for y the value f of x, nor could we substitute in x the value for f at y. Right? In either case, attempting to solve for x or y is not going to lead us to a functional relationship that explicitly describes the unit circle. All right? So this is an example of an implicit relationship. Now we know in the first case we can apply the derivative operator to both sides. In the case for an implicit relation or explicit relationship, we can apply this derivative operator d dx to both sides of this relationship. And we know on the left-hand side, if we apply the operator d dx to the value of y, that's going to result in dy dx. And if we apply the derivative operator to the right-hand side of that quadratic, it's going to produce the result 2x plus 3 from our fundamental derivative rules. The left is just an example of notation, dy dx. The right is an example of the application of our rules. And what we end up seeing is that dy dx is equal to 2x plus 3. Right? However, if we apply that same operator to our unit circle, if we apply that d dx operator to both sides of our unit circle so that we have d dx of x squared plus y squared on the left and d dx of the quantity 1 on the right, that operator will still apply itself, right? And it won't change the value of the equality, right? It won't change the fact that we have an equality relationship. And we know that, for instance, when we apply it to the right-hand side to the constant of 1, it's equal to 0. And when we apply it to the left-hand side, it is going to distribute across the sum. When it distributes across that sum, we know the derivative for the first term in the sum, the derivative of x squared with respect to x is going to be 2x. And the derivative with respect to x for y squared, however, is going to be maybe a little perplexing to us at the moment. This is asking for the derivative for the variable of x, where we're applying it to an argument that does not involve that variable. We're applying it to the argument given by y squared. All right, sorry folks, I was interrupted. Now, this derivative with respect to x for y squared is where we're going to have these implicit methods occur. All right. If you noticed, everywhere else, the derivative operator has applied itself. Right? The derivative with respect to x squared we know is 2x. The derivative with respect to x for 1 we know is 0. The only derivative we don't know how to apply is this value here, because it is being applied to an implicit description of a functional relationship with respect to x. What we think about here in its application, this value of y can almost be considered to be an implicit relationship with x, in a functional relationship where we might consider that to be kind of unknown at the moment. We can kind of assume that it is in our implicit methods, and that's how we kind of start tackling this calculation implicitly. All right, if we bring this in to note here. Right, again, to begin with, I said to evaluate the derivative with respect to x for y squared, we have to perform what's called implicit differentiation. And what is going to be useful is a chain rule, because the way we're going to think about it is y is going to be thought of as some implicit, being in some implicit relationship with the variable x, right? To be able to take its derivative with respect to x. So here it is known from chain rule, right? If y equals f of u and u equals g of x, right? We know from chain rule dy dx, the derivative with respect to x for what would be just a function of u in this case, with this setup for y, would be dy du times du dx, right? And this all comes from the second version of chain rule. Right? Well, we know that value of dy du, if y is equal to f of u, is going to be equivalent to the value we call f prime of u, or the derivative of u with respect to f at u. And the value du dx, right, it is going to be the derivative. I should probably indicate this. It is going to be the derivative with respect to x for g of x. Right? It is going to be this value we might think of as being g prime with respect to x, but also can be just considered the value of u prime with respect to x as the derivative of u with respect to x, right? And it can be concluded using the chain rule, then, that the derivative with respect to x for f of u, borrowing this notation here for dy dx, can then be expressed this way, where we're substituting in for dy du, the derivative with respect to u for f of u, and that's going to be substituted in here as the second factor, and du dx, we're going to substitute in for the value u prime right here. And this becomes our fundamental understanding in implicit differentiation. And that is, if I take the derivative with respect to x for a function that is of some other variable, here we're using the dummy variable u, right? U is just playing the placeholder of any other variable. It could even be variable x, but that would be explicit. We're looking at implicit methods, so u is representing just any variable other than x. And what we can find is if we take, right, its result, it's going to be equal to what we would say is the derivative of that dummy variable u times what's going to be the derivative with respect to u for what is going to be that function expressed in terms of u. All right. We can say this in terms of y, as we see here, right? And this is actually how we'll probably see it applied more often in implicit differentiation when working with the relationship between variables x and y, right? And that would be when we find the derivative with respect to x for some function of y, which notice, that is what we're asking for up here. The derivative with respect to x for a function of y, where function of y now is y squared. And what implicit results say is that this is going to be equivalent to y prime times the derivative with respect to y now for that function of y. If we set that up for the case of the derivative with respect to x for y squared, f of y is going to be y squared, and the derivative with respect to y for y squared is going to be 2y. And when we think about the derivative with respect to x for y squared, it is going to be y prime times the derivative with respect to y for y squared, which we just identified above as equal to 2y. So this is going to be y prime times 2y, or just the value we note is going to be 2 times y prime. Right? Where we think about y prime is representing dy dx. Maybe we should say that here, where y prime is equal to dy dx, right? It is that derivative of y with respect to x. It is representing that instantaneous rate of change in y with respect to x, or that slope of the tangent line for what would be the relationship between y and x. Just be careful there with instantaneous rate of change. We've yet to really talk about that in our notes. So in the implicit result, right, if we go back and substitute in for these quantities, 2x plus the derivative with respect to x for y squared equal to 0, the value of the derivative with respect to x for y squared being equivalent to 2y times y prime, we end up with this result right here. 2x plus 2y times y prime is all equal to 0. And as we noted above, this is why I spent the moment noting this y prime is the derivative of y with respect to x. And that equation is simple enough that we can solve for that value. And that is the next thing we do here. Solving for that y prime, which equals dy dx, the derivative of y with respect to x will end up being revealed, right? And it's going to reveal itself implicitly as a relationship with both x and y. Right? We see that being noted up here. So if we take the above statement here and we solve for y prime, we would subtract 2x from both sides and then divide by 2y on both sides. And we would end up with y prime equaling negative x divided by y. And what that represents is the slope of the line tangent to the unit circle at the coordinate x comma y. That slope is described by dy dx, which equals the opposite of x divided by y. If we place ourselves at any point on the unit circle and we're interested in what's the slope of the tangent line, we would take the coordinate we're placed at and calculate this function, or this value, I should say, for the value of y prime. We would take the opposite of our x coordinate and put it over our y coordinate. We consider doing that in the unit circle. So at 1/2 comma the root 3 over 2 on the unit circle, the slope of the line tangent to the curve is actually given by the opposite of, and here's our value of x, right, being placed over our value of y in that ratio. And that does simplify to negative 1 over root 3, or negative root 3 over 3 in value. And if we were to sketch our unit circle and place ourselves at this coordinate, we would see the slope of that tangent line. Right? We would see the slope of the tangent line would match that value. Or at least it would be a negative slope. It would be a negative slope where if we kind of interpret it here, right, it would drop 1 and run forward a little more than 1, because the square root of 3 is stuck between 1 and 2. So it would have a slightly shallower slope than a slope of just negative 1. All right, in our interpretation. But what we did find is we did find dy dx to be this implicit relationship between x and y, and we found it through the process of applying implicit differentiation on this unit squared equation. All right. If we summarize that procedure, this is how we summarize the procedure for performing implicit differentiation. We can kind of summarize it with these three guidelines. Right. Hey there. Sorry, folks. Let's backtrack just a little bit. You'll notice here I changed the notes just a little bit. Let me make note here. I did want to add an illustration into that last example here, this initial introduction to implicit differentiation. Again, I want to try to give purpose from this example. So this is our purpose. This is the reason we use implicit differentiation the way we do. We do have the case here where we're working with this unit circle. And if you remember anything about functional behavior, functions, right, their graphs will pass the vertical line test. Well, this graph will not pass the vertical line test. A unit circle does not describe a functional relationship between x and y. You certainly can isolate the top half and the bottom half and talk about them functionally. But overall, the unit circle is not a functional relationship between x and y. And we can see that in the graph. But we can still find the slope of the line tangent to the curves on this implicit relationship between x and y. So we can still go to different coordinates on this graph. And here we were just looking at in this example the coordinate 1/2 comma root 3 over 2. That would be this coordinate on our graph at x equal to 1/2 root 3 over 2 for y. Pardon me, folks. I'm getting a phone call. I got to take this. All right. Sorry, folks. Had my dad calling. I had to take that call. Didn't want to have to call him back here by the time I finished this. So, yeah. Again, here, all we are illustrating is that slope of the tangent line here at this point. And we can find that for non-functional relationships, for curves in our two-dimensional space that aren't necessarily summarized with a functional relationship, right? The curves don't have to pass the vertical line test for us to be able to determine the slopes of the lines tangent to those curves. We can use the method known as implicit differentiation to find those slopes. Now, you will have slope descriptions themselves that are also implicit. Notice here we do not get a functional description, a function of just x that describes our slope, as we had done with the case for the explicit relationships, right? Here we would do also, in most cases, end up with an implicit relationship also describing the slope. So not only do you need to know the x value where you're interested in the slope, you're also going to have to know the y coordinate, right? Where you're going to need to know the slope, or where you're interested in finding the slope of the tangent line. All right. So I wanted to include that illustration before we moved on here. Now, when we do move on, again, how do we apply this technique? Well, you do apply d dx to both sides of the relationship, right, between variables x and y. And when you apply it to both sides, you're then going to have to evaluate all your derivatives for functions of x with respect to x, and that happens with all the rules that we've developed up to this point. And you are going to encounter cases where you're going to have to apply that operator to functions that are stated in terms of other variables, like y squared was the square function stated in terms of the variable y. And we were interested in finding the derivative with respect to x for those functions of y. Where when we consider that derivative, we just want to keep in mind in our implicit methods that that derivative is equal to y prime times the derivative of f of y with respect to y. The result I have highlighted here on the right-hand side. Now, once we make this assumption and have our value of y prime appear within our relationship for the derivative, I can then solve for that y prime, which is going to give me that slope of the tangent line, dy dx. Now, it will state it implicitly in most cases. Let's consider finding dy dx or y prime when we have y cubed plus x cubed equal to y squared minus 2x plus y. When we have this implicit relationship. Notice attempting to solve for variable x or y would be really kind of pointless, right? We could put in a lot of effort and probably not be successful at all. Where the time could be spent finding dy dx could be by performing our implicit derivative techniques, right? And if we can't express this as a function, it will go that direction, right? So we might as well begin that now. So if we apply that derivative operator to both sides, this will be our first result. Right? We apply it on the left to y cubed plus x cubed, and we apply it on the right to y squared minus 2x plus y. On the left, we would have this result, and on the right, we would have this result. And when we distribute the operator across the left-hand side, it will distribute across that sum to each of the terms, and it will behave similarly on the right, distributing to each of these terms. Now, we have determined some of these already, like the derivative of y squared with respect to x, we know is y prime times 2y, or 2y prime. And we have indicated above that if we think about the derivative with respect to x for just y, that's just dy dx, or y prime also. Where we need to determine the derivative with respect to x for a function of y that's probably new in this result is for the case of y cubed. All right? And if we apply our implicit methods as we had set up here, as we had noted, this result is 2y prime. This result is going to be y prime. The derivative with respect to x for 2x is 2, and the derivative with respect to x cubed is 3x. All we're left with is the derivative with respect to x for y cubed, where if we follow the implicit rule, this idea seen here, it is just going to be y prime times the derivative of that interior function y cubed with respect to y. And what is that derivative? Well, that derivative would be 3y squared. So that results in 3y squared times y prime. And this becomes our implicit relationship. I do note this is all because, and I work through each of those individual implicit derivatives. The derivative with respect to y cubed is this. The derivative with respect to y squared is this. And any derivative with respect to y is this. All right. Substituting those into the above results here, here, and here, along with our derivatives of functional behaviors here and here, we end up with this implicit result for y prime. Now, once we obtain that, the idea is we need to solve that for y prime. And we can see that we actually have 3 terms involving y prime, 1 on the left and 2 on the right. So typically the way that you solve if you have multiple terms involving y prime is you will gather all the terms involving y prime to one side of the equal sign. All the terms not involving y prime will be brought to the other side of the equal sign using some of our algebraic properties for equality, the addition and subtraction properties particularly. That will then be followed with a little distribution property on the side with y prime, factoring out the y prime from both terms, and then dividing by what is left after we factor out the group that's left after we factor out y prime on both sides. Let me illustrate here. All right. We can move one of these, well, these terms involving y prime to one side and these terms involving just 3x and minus 2 to the other. I don't remember how I do it in the notes. Let's see how I perform that in the notes. Okay, I move all the y prime terms to the left-hand side. So that would involve subtracting the 2y prime and the minus y prime from both sides. And I move the 3x to the right by subtracting it. All right. Now, with that order, I can now factor out a y prime on the left-hand side, leaving behind this group 3y squared minus 2y minus 1 times that y prime. Dividing both sides by that group, I can now solve for y prime. I get my solution, implying that y prime in this case is the implicit relationship given by negative 3x minus 2 all over the quantity 3y squared minus 2y minus 1. Now, do I need to have that in a grouping symbol? Most likely not. Let me bring that out, actually. Clean that up just a little bit. We could just say it that way. But that's illustrating the division. All right. And I do think I make that as a final statement down here, too. All right. Let me clean this up. All right. Thus, for the implicit relationship we started with, the implicit derivative is given by this statement. For this implicit relationship, where we know we don't want to try to solve that for y, and we didn't have to spend any time doing that, it would have been fruitless because we can see here our derivative is itself an implicit relationship. So inevitably, we were going to be forced into implicit differentiation. And this describes the slope of the lines tangent to the curve above, where that curve above is not going to pass the vertical line test, most likely, right? Very likely, right? We know that because of this implicit result. All right. Now, let's look at another example. Here's a little bit more complex situation. A lot of this is trying to illustrate to you. And you can see where the algebra, right, is going to slow you down. And that is where you're solving for y prime, right? Besides that implicit differentiation in here, the other trickiness of the problem does come from trying to solve for y prime. That does require some strong algebra skills. Right? If we take this implicit relationship here, the square root of x times y minus 4 equal to x minus y squared, and we apply that derivative operator on both sides. On the right, we can see it is going to apply itself to both the x and the y squared, where we know both results. This is going to be the derivative of that is 1. And the derivative of y squared, we know again is 2y prime. We have determined that derivative on several occasions now in this set of notes. If we focus our attention actually on the left-hand side to begin with, right, what we will notice is we do have a derivative with respect to x for the, the 1/2 power of the quantity xy minus 4. Where if we apply our derivative operator to that statement, right, using a little bit of that power rule, and specifically the power rule for functions in the form of a chain rule, the result is, right, the derivative of the interior, xy minus 4, that's the statement right here, times the exterior function's derivative, where you bring out the power of 1/2, and you take your old function, your old interior xy minus 4, who you're finding the derivative of outside the function, and take its power now and decrease it by 1. That would drop it down to negative 1/2. Where now we're just faced with finding the derivative with respect to x for xy minus 4. Now that derivative operator will distribute across the across the difference to the xy and the 4. We'll see this operator, where we know the derivative of the constant at the end is equal to 0. So I'll just have that's this minus 0 in the next step. The beginning of the next step, though, starts looking at the derivative with respect to x for x times y. Now, to approach that using implicit differentiation, you do have to approach it with a little product rule. Y is not a constant. Y is also a function, null behavior. A functional behavior where you're going to apply the derivative operator with respect to x in a product rule with x. So it is the derivative with respect to x for the first factor x times the second factor y, and added to the first factor x times the derivative with respect to the second factor y with respect to x. And we have found this derivative before, and we know what the derivative with respect to x is. The derivative with respect to x is 1, and this derivative we found before is equivalent to just y prime. So here we have y plus x times y prime for the derivative found on the left-hand side of our implicit differentiation. On the right-hand side, we had noted that result is 1 minus 2y prime. Right? Oh, and I ought to be careful here. What we just found above with this y plus xy prime, we just found the derivative with respect to x for that. Oh, I should be careful there. That's not that radical. Let me say this. So I think it gets a little mashed up here. Equals y plus xy prime and thus d dx equal to this further implies, let's replace this because we know that this is now this. Right, is equal to this derivative on the right-hand side. There we go. I think that might make it a little less muddled. Because we are finding derivatives within implicit derivatives here too. We have a couple layers of some chains happening, compositions, with multivariable relationships, implicit relationships. All right. Now, finding those derivatives on the right-hand side, we have 1 minus 2 times y prime on the right. And here is our implicit derivative expressed implicitly, right? Where y prime is actually involved in this term buried inside of this group and this term here on the right-hand side. And again, as we've noted, if we have multiple terms involving y prime, we want to try to group those terms to one side. This grouping is going to be a little bit more complex. All right, let's see how I handle it here. Okay, so on the left-hand side, I do clean it up a little bit. I do note, to begin with, that this quantity here is equal to this quantity here, which allows me to break the numerator apart across that common denominator and make this statement here. So here's my y prime term isolated right here. And it is a ratio term. I'm going to group it with this 2y prime here on the right that we're subtracting from 1. So I'm going to add this term to both sides, and I'm going to subtract this term from both sides. Right? I'm going to add that 2y prime to both sides, and I'm going to subtract that y divided by 2 times the square root of xy minus 4 from both sides. Now from here, I'm going to factor out the y prime from both these terms and then gather them into a common denominator in that group with y prime factored outside that group. So that's what I have going on here. I have factored a y prime out of this group, right? Leaving behind a 1 up here and a 2y, which to bring in a common denominator, right? I'd have to multiply that numerator 2y by 2 times the square root of xy minus 4. So that, when added to the 1 in the numerator here where y prime would be factored from, we end up with 1 plus 4y times the square root of xy minus 4 in that numerator. On the right, if I combine like terms, 1 is this quantity over itself, where we subtract y from that quantity in the numerator, and we prepare this item. Now, with y prime factored from this group on the left, it being a ratio, to divide by it, we could also just multiply by its reciprocal on both sides. So when I do that, I'll isolate the y prime on the left, and on the right, I'll have that factor multiplied by the reciprocal of that factor on the left. And you'll notice in that reciprocal, these two quantities cancel. The 2 times the square root of xy minus 4 is a common factor. So when they cancel, we'll be left with the quantity 2 times the square root of xy minus 4 minus y in the numerator, all over the quantity 1 plus 4y times the square root of xy minus 4 in the denominator. Right? And thus, we might go on to just conclude here. I did not do that. This is our final example, so let's make note. Thus, 4, let's go back to our original equation and identify it again, because this is kind of a distance away, right here. We just found y prime was equal to this implicit relationship right here. Oh, rather complex implicit relationship. The above example doesn't illustrate some very complex calculus and algebra. Right? And I shouldn't be too discouraging there when I use the term complex. It is complex, but it can be tackled in a systematic manner, right? Where in that systematic manner, we can break it down into its simple parts. And that's what we see us performing here in this calculation. Right? This is just an introduction to implicit differentiation. We're going to see a couple more examples in class, most certainly. And then we're going to come back and actually see this idea applied in the case of some specific functions that we're familiar with that have inverse relationships with one another. Exponential and logarithmic functions, and trigonometric and their inverse trigonometric functions. All right. We're going to come back and look at this technique used there. And then also, like I said, we're going to continue to look at that fundamental rule that we developed in this set of notes. All right. If we think about that fundamental rule, where is that? That's summarized down here. In terms of x and y, that would be that the derivative with respect to x for any function of y, where we think about y being in its own functional relationship with some other variable, well, that's given by y prime times the derivative of y, the derivative for that function of y with respect to y. Right? We're going to see some more usefulness of this rule put into play. We did develop what we might say is the beginnings of that right here. Right? Here we're illustrating a couple of specific cases for power rule. For a power rule of function y, where we're taking the derivative of that function y with respect to x. And we see a result very similar to what power rule would give us. Right? But in terms of y, where we have to bring in also this factor of y prime in each case. Right? Take note. So that's where we're going to also see some implicit methods develop for us in an interesting way. I'll say it that way for now. All right? But yeah, folks, that is all I have for you in this video. We were going to come back and use this implicit technique again in some future notes here, right, in some future lectures. So expect that, and in some future videos we're going to come back to this idea and bring up implicit differentiation now in our study. So we have to be prepared for that. So with that said, I'll see you in that next video.